All right, so we're going to have the shortest lecture ever, okay? I just want to finish what we've done with wavelets and before we move on to video. So video will start on Thursday, and basically we have, I think 3 lectures left, really, 3 handouts left, but they're quite short on video, okay? So this is the last bit on images. And now from now on, we're going to move on to video, and we're going to look in particular at motion estimation, and MPEG. So I wanted to finish with the with wavelets, and there's 2 little bits in the handouts I didn't cover, and maybe wanted to look at what was in the tutorial to see what could be at the exam. Right. So the first point is about the wavelet transform and denoising. So what you have here on the left is the Legal 5.3, I believe, discrete wavelet transform for Lena. And so you can see, so remember it's the same as Haar transform, except instead of using these filters you've been using, you have now a different definition for the filters. And so this is what you get. So it's very similar to what you have in Haar as you've seen it. And on the right hand side, so what you have is, sorry, how come I don't have the sorry, display, zoom, full screen, page. No, it should work. All right, so on the right-hand side, what we've done is instead of doing the transform for just the picture of Lena, what we have is the Wavelet Transform for just noise. Okay, so we just took we generated some Gaussian noise, white noise. So that means that so we set it from a black image, for instance, and what we have is for every single pixel, we generate a random number following Gaussian distribution, and we see how we can compress that, or how we can transform that. And so this is the transform of the wavelet transform for that. As you can see on the left, this is very good for compression because your signal indeed after transform, you have loads of zeros everywhere. And that's the whole point of compression, is that you generate a lot of zeros, or near zeros. But when you look at noise, basically every single subband is still noisy. Okay, so you have the same amount of signals in every single subband. And what it tells us is that well, the first thing is you don't compress noise very well. Okay, so if you have a noisy image, if you want the worst case scenario for you of a signal to compress is white noise. Okay, so if you do work in audio, that would be the same. If you just have just a soundtrack, audio sample with just white noise on it, it'd be very hard to compress. And same here, if you work with the picture, if all what you have is film grain, or just noise, then it's very hard to compress anything, which makes sense, okay? Now, we've seen that as well with the Fourier transform. We looked remember in the Fourier analysis, we looked at the Fourier transform of a noisy signal, and what we get was a flat power spectrum, okay? I don't know if you remember that. So we looked at the power spectrum of just noise, then it's just a flat, so it means we have high frequencies. There's no peak in the frequencies, okay? We use the whole spectrum, use the high frequencies and the low frequencies in the same way. So 2 things. So first, okay, noise is bad for compression. So if you have a noisy picture, it's very hard to compress nicely. And second of all, maybe we could use that space to do denoising. Okay, so the same way we looked at the Fourier transform, and we looked at I briefly mentioned the Wiener filter. To work, so the idea would be to work in the transform space to be able to do the denoising. And so this is what you get. Okay, this is the histogram of your coefficients. Okay, so so in red, the dotted red is the values of the coefficients for around 0. So you have a lot of coefficients that are close to 0. Sorry, so that's kind of the very peaky version that you're looking for. And for the noise, what you have is more like a flatter Gaussian distribution. Okay? So what we observe is that you have what is typical of a real signal is more this kind of compact version and not this spread out version. So the idea would be to say, if you see coefficients that are high in value, then most likely this is due to noise. Okay, it's kind of rule of thumb. You probably, if you look here at the high band, okay, the high band, you can see it's mostly zeros. So if you see something like that where there is lots of high values, then maybe a way of denoising would just be to shrink these values and say if you have a high coefficient, then maybe we should just reduce the value of that high coefficient. And this is called wavelet shrinkage of wavelet coring. That's the idea of you transform your picture and you look at the coefficient and you're trying to change the value of these coefficients. So this is two ways of doing that. So on the left, okay, so you have a kind of hard threshold, and on the right you have a more soft threshold. So, all right, so what's going on here exactly? Okay, so on the x-axis you have the input coefficients. Okay, so that after transform you look at the values, what you get, that's a value. So the values here range from -50 to 50. And then that's the output you have after this, this shrinkage. So what we're trying to say here is like if you have a value within some range, so here it's between -30 and 30, you're trying to say if you have, if you have a value of -20, that's kind of unlikely value. So I want to say that's actually 0. Okay, so you say any value in between -30 and 30 now is transformed into 0 because coming back here, we know that most of the values are either 0 or high. Okay, they're not quite in that middle range. Okay, so here's what you say. We say if you have a value which is a small value but non-zero value, then we set it to 0. And if you're outside that range, okay, if you have a very high frequency, then that's probably stronger than the noise, and therefore you want to preserve that, and therefore you don't touch it. Okay, so we say if you have an edge, that will create a high coefficient, and you want to preserve that high coefficient. Okay, so if your edge is stronger than the noise, then you just want to preserve it. Does it make sense? All right. Now this is a bit strong, so usually you go more for kind of a softer threshold version like that, where you don't have this edge effect here, where a value is either going to be set to 0 or kept the same, so you have more a gradation in the process. So the process goes as follows: so you apply the transform and you apply this kind of it's called coring or a shrinkage on the coefficient, and then you get denoising. And this is what you get if you apply straight as. So on the left you have the noisy LEDA. So I just added some noise to the picture, and here's after this process denoised a bit. You still see a few bits and pieces of artifacts. Okay, obviously here, it's not going as well as you'd like, and you can see remaining effects here. So it's not perfect. It's actually not as good as Wiener. Wiener will be much, remember, it's much better on that. So it turns out, okay, you need to do a bit more to solve the problem, and one of the aspects is we need to use something called undecimated wavelet transform, and we'll talk about that just after that bit. But anyway, it's still at the core, like if you do enough changes to this core idea, you can get pretty good results, and in fact, it's one of the two techniques that people use. So either you use wavelets or you use Wiener filter. It's kind of the two main techniques you have out there, and these are the kind of de facto standards in the industry. People tend to use wavelets, and I don't really have good examples here, but that's because the artifacts it generates are less noticeable than the Wiener filter. So remember Wiener filter, you have to have this split into blocks, and you have all these frequencies going on, you have maybe ringing artifacts and so on. So in wavelets, it's a bit more natural. I wanted to this, so okay, so just keep in mind, the only thing I want to say here is like, okay, this nature of noise, so noise is back for compression, and the fact that you can then work in the wavelet domain for denoising. So here comes the last piece of theory on wavelets you should be aware of, okay? Is that, maybe come back to the good old diagrams we have at the origin. Right, so this is kind of the heart of it, okay? In this diagram, remember, like we looked at the perfect reconstruction, and we say you have this right balance. You have these two equations that says, if you have some relationship between the four filters, the analysis filters and the reconstruction filters, then you're good to go. You know that the input would be transform and transfer back, and so you've got the reconstructed output is the same as the input. And that's great. But remember what's going on here, okay? You have all this downsampling operation and upsampling operation. And remember that downsampling creates aliasing, okay? So that's kind of the risk there. And in fact, we kind of know that's going to create aliasing because H1, it's a high-pass filter, okay? So it's looking only at the high frequencies. And now you're going to apply downsampling operation here, right? So it's a bit mad. You have a picture, and what I told you time and time again is like if you want to downsample your picture, you first have to do a low-pass filter, use a sink or something equivalent, okay? And now what we're doing here is we have the picture, we take a high pass, we only keep the high-level frequency, and then we can downsample, okay? So surely there is a lot of aliasing here, right? I mean, we're totally aliasing the picture here, right? And that is true. We are doing that. What the perfect reconstruction filters, so the perfect reconstruction conditions tells us is that, yes, we're going to do aliasing here. Everything will be messed up. But somehow, by the choice of the filters we have, everything will be perfectly reconstructed, okay? And so it's important to realize, okay, we can't achieve perfect reconstruction, but we have aliasing, and the aliasing is in the coefficients, okay? So the coefficients are aliased, okay? So aliased in the sense that you have this subsampling replication of the everything going on, okay? So the coefficients themselves, after downsampling, are not pretty to look at, okay? They will change dramatically, okay? So aliasing occurs, but it's in the coefficients. All right, so this is a very important point. So come back to this remark, okay? So this is what I say, okay? So so the high-pass filters are downsampled, and we have, it's not a problem, it is a problem, okay? but it just works out mathematically because we invert all that very carefully, okay? So it's just like all the equations are just very tight, and we just come back by miracle, if you want, back to the reconstruction, okay? So one aspect which is not really nice is that when you use the discrete wavelet transform, is that when you just look at the analysis part, and you don't do the reconstruction, what you end up with, so the coefficients, are it's a shift variance operation. Okay. So remember what shift invariance means. So you've seen that with the convolution. Means that you have your input. If you shift the picture by say a pixel, and you apply your process to that picture, the result is the same as if you shifted the output by 1 pixel. Okay, so shifting the picture doesn't have a dramatic effect on the results on your process, but here it will. Okay, so this is a little animation that will show you that what's going on here. Okay, so so we're looking at the level 1 analysis filter from Legal 3.5 or 5.3, I forgot. So the red line is it's just in 1D. Okay, we're looking in 1D here. So what you have is the so we're looking at 3. So the input is in blue. Okay, so that's a button here. That's the input, and that's the coefficient you get given your 2 filters, so the high and the low filters. Okay, and after a decimation. All right, so that's fine. But let's look at what happens when you shift the input signal by a few pixels. Okay, you can see that. So I'm going in time here, and the only thing I'm doing is shifting the input, the blue input, okay, by a few pixels. With convolution, the look, the appearance of the shape of your coefficients would be still the same, okay? So you'll just be translated version of the filters. But here you can see it's just way more than a translation, okay? In fact, the coefficients, if you just look at the red one, they change, it's quite dramatic change in the shape of your coefficients, okay? So that's a very important point here I want to make, is the discrete wavelet transform is not shift invariant, okay? It is shift variant. And that's what it means, okay? So you have to remember what it means. It means if you shift the input, the output is not just the shifted version of your previous results, okay? And that has a whole range of issues to do with even with compression and so on, okay? So if you come back to what we say, so the coefficients are earliest, okay? So that means that when you start to look at the coefficients, if you want to do analysis, okay? If you want to just, say, I want to do phase detection, and you say, I'm going to use the discrete wavelet transform to be in a space where maybe you can do some machine learning. The problem is, if you have just a slight shift of your picture by 1 pixel, then the results of the coefficients, like the value of the coefficient, will change dramatically, potentially, okay? So that's a bit of a problem for your analysis, because it means like you're looking for stable feature vectors, but here the feature vector will actually change quite a lot depending on very few, that's just 1 pixel changing or the position slightly changing. The other problem as well, so that's one thing. So for analysis, a bit of an issue. The second aspect is for compression, which is a problem for compression, is that the perfect reconstruction works if you don't do anything to the coefficients. Okay, so as long as you don't touch the coefficients, you're fine, you come back on your feet. Obviously, if you change the coefficients, then what happens is that all the perfect reconstruction mechanism and so on falls apart, and all bets are off. Okay, so you can generate quite a lot of artifacts, and if you, for instance, shift your picture by just 1 pixel, the results, the artifacts you get might be completely different as well in appearance. Right? So something to keep in mind, that it has a profound impact. So something that's not in the handout too much. Well, it is actually very briefly here. So the solution to that problem. So for the way we approach that in compression is, remember, you have a pair of analysis filters and reconstruction filters, and so what you want to do usually is to find the correct order in which you take them, because if you destroy the coefficient, then maybe you want the artifacts to not be that visible, okay? But the real way you can solve that, and say if you want to use for denoising, is to use undecimated filters, okay? So if you come back, sorry, to this, if you come back to this filter bank, okay, of trees, so you have your input and you have all the different levels. What you can do is, if you want to remove all these downsampling operations, okay? And so instead of having the nice little tree you have here, where basically the transform, okay, in the discrete Wavelet transform, the amount of coefficients you get is the same as in an amount of pixels you had to start with, okay? So you don't increase the amount of, like the number of coefficients is the number of pixels, right? But what you could do is like to say, well, I don't downsample these, and so instead of having here 4 quadrants, you actually would have 4 pictures, okay? So you would say one picture is just a low-pass version, the low version, but that would just be the entire picture. And then the high-pass would actually be the entire picture and so on, okay? So you could say, I don't do the downsampling part, okay? So if you don't do the downsampling, you don't have aliasing problem, and everything is fine. The only problem, of course, is like now you're looking at level 1 Haar transform, and you multiply by 4 the amount of information you have. Okay, so you have 4 times the number of coefficients with that, and if you have a level 5 or level whatever number level, then you increase by quite a lot the number of coefficients you have. Does it make sense? All right. So if you don't downsample, you still shift invariant because all what you're doing is just normal filtering. And it's all fine, and you can, that's what you do denoising and so on. You can do analysis, you can do a lot of things. But the problem you have is you increase the amount of coefficients you have, and now, you know, instead of having one picture in memory, you have maybe 20 different versions of that picture. Okay? So that's one solution. And that's actually what is used in denoising. So in denoising, people use sorry, say that again. So they use undecimated. So that's the word here. So undecimated. So undecimated means you don't have the downsampling operation. And so in denoising, they do that. So they used undecimated version of your wavelet transform, so you don't have all these aliasing issues. There are techniques, so there are a plethora of techniques. One of the techniques they're trying to find a nice trade-off to keep a balance between, reasonable balance between the number of coefficients you have and the problem of the shift invariance. It is dual tree complex Wavelet transform by Nick Kingsbury, which is something where you basically only have, you bound the amount of, you can still have multiple levels, but you only bound it to 4 times the number of pixels you have. All right? So I say that again. If you have undecimated, because of the shift invariance, downsampling is a problem if you want to work on the coefficients. And so a way of getting around that is to remove these downsampling steps and to work with undecimated version. But then the number of coefficients goes as 4 times the number of levels times the number of pixels. So you basically have quite a lot of increase in the data you have. Okay. So that's the drawback for it. But there are some techniques out there that can try to work around that. But they're quite obscure and arcane techniques. Okay. So that's pretty much it for the Wavelet Transform. So this is the whole bulk of it. If you look at the tutorial and previous year exams, you'd find that there'd be stuff on. So this is from the tutorial. So you have these diagrams. So these diagrams, you should be able to make them, right? To just look at the diagrams, identify what the analysis, the reconstruction, and so on. You need to know what the perfect reconstruction conditions are. Be able to know which one is which. So that's actually, who knows the names there? So the first one, what is this one? So there's two names, okay? There's one called the no distortion, and the other one is called the no aliasing. So if that's a no aliasing, or is that a no distortion condition? No distortion, right? The simplest way to think about it, okay, is if you have a minus z here, okay? So minus z is definitely the sign that that's a replication. That's that's the aliasing part of your signal. Okay, so remember, if you look at the slides, the downsampling operation creates the replication, and in the equation, the z transform, basically you have the h of minus z in the equation. Okay, so if you see minus z, it's to do with aliasing. All right, and in this example here, you're asked to basically do simple stuff. You just have to plug in this polynomials in Z, complex polynomial, and just make sure that indeed the condition is correct, and so on and so forth. Okay, you don't have to do that now. Something I leave that for you for home. All right, so that's it for complex Wavelet Transform. There's lab tomorrow. I still have to write it. And after that, we're going to start working on motion and video compression.